Hello everyone, welcome to the second part of the introduction to Simulink and modeling of the feedback controller. In the previous lecture we talked about sources and sinks as two most important blocks in Simulink library. We talked about different signals such as sine wave, step function, step input, and also random signals. We talked also for sync, we talked about the scope and workspace and how we can apply them. In this video, we will talk about other blocks while we are making our simulation model, simple simulation model. The other important category of blocks that we are interested in is the math operation block. This allows us to perform basic math operation on signals, for example, adding, subtracting, multiplying, or dividing signals. To implement a feedback loop, we naturally need to subtract the current state of system from the set point to generate the error signal, and we will implement control action around that error. Therefore, we click and drag subtraction block over the over our Simulink window. So here is the subtract signal. We connect the step to the subtract. To ensure proper feedback implementation, we connect our set point signal to plus terminal of the subtraction block, and the state signal being feedback to the minus. But we will do it later. Recall that the contact block in the Simulink, you can either click or drag the arrowhead of one block to the other one, or we can actually keep the control, hold the control, and then click on the block that you want to connect it to. So if you wish to add a disturbance, you can do it, but in this model, we just keep our model simple and we don't go to the disturbances. Another important or next category of block that we will examine is the continuous blocks. As the name suggests, these blocks provide a means of modeling continuous system. More specifically, they provide function for transforming continuous signal within Simulink. This section will provide the bulk of our model structure. For this lab, we care about three blocks, which is PID Controller, the other one is transfer function, and transfer delay. These three blocks will provide the control action, linear transfer function, and dead time simulation capacity respectively. So to construct our core feedback loop, we start by dragging over a PID controller block and connecting it to the output of our subtraction block. This represents the transformation of our error signal to input signal. Next, we add the transfer function block to our window and we connect the PID controller to the transfer function. This represents the gain and time constant portion of our first order plus dead time model. Conceptually, it also represents the transformation of our input signal to the output signal. It can be level or temperature without time delay. Finally, we drag over a transport delay block and connect it to the output of the transfer function. So this will provide us theta or dead time portion of our model. To close the loop, we then connect the output of the transport delay block to the minus symbol of our subtraction block, like this. We will now examine each of these three continuous blocks specifically more in detail. Let's double-click the PID Controller block. It will bring up PID parameter window. As you see here, the first thing we note that a Simulink brings a formula to our attention. So this is the controller transfer function, which we have a proportion part, integral part, and differential part. So we have proportional, p, integral, deviation, derivative, and also we have coefficient n. N is a fourth tuning parameter that we will not deal with in this lab. Essentially, it is a means of approximating the deviation of the error signal. So since it is impossible to simulate tau ds exactly, so we just put 100 as the default of the Simulink. It's 100. We keep it as this. The next important thing that we note is that while we are able to input our controller parameter directly, Simulink access to the MATLAB workspace. So by writing a script in MATLAB, Simulink would also access to that information. So for now, we will suffice to define everything by parameters as variables. So instead of inputting numbers in proportional, integral, and differential derivative, we just put a variable, and then later we will define it in the MATLAB. So now, instead of proportion, I would say kc, and we defined it later. And then instead of integral part, I would say kc tau I. And instead of derivative, I would say kc multiplied by tau d. And we have to be careful that when we do changes, we click the apply and then OK. So it would be saved. What about the theta? We know that but before the theta, we have the transfer function. So once we are done configuring our controller tuning parameter, the next step is to limit our possible, the parameters that we have, because usually in real life, for example, if we have a valve or we have pumps, they have some maximum and minimum possible outputs. But how we can define this output? The thing is that in previous version of MathWorks, PID controller didn't have something for this purpose, so we had to add a block with the name of saturation. But since the PID controller and saturation block are frequently used together, so the recent version of the MATLAB, which is 2016b, includes both of them and combine these two functions together. So to limit the output of our controller in MATLAB, we start by clicking the PID Advanced, and then we will see we have output saturation and limit the output. By clicking this, by checking this box, we will see that the upper saturation limit and the lower saturation limit options will be unfaded. So unfaded, and then we can put 15 and minus 15 instead of the limits that we have. And then we apply, and then we send OK. Now let's go to the transfer function. Transfer function block, as its name suggests, allows us to simulate linear transfer function within Simulink. So we double click on the transfer function block, and it brings up a transfer function parameter window. And in this window, we can set the coefficients of numerator and denominator of the transfer function. Simulink assumes a fully expanded transfer function. What this means is that each extends a successive entry in the numerator and denominator vector correspond to decreasing power of s. So, for example, if for numerator we have for 3 2, 1. And for denominator, we have 6, 4, 6, 5, 4, 3, 2. These are the denominator coefficients. As a result, we will have a transfer function as 4s3 plus 3s2 plus 2s plus 1. And then in the denominator, we will have 6s4 plus 5s3 plus 4s2 plus 3s plus 2. But similar to our PID controller, it is desirable to simplify our transfer function in terms of variables. So we just defined, because we know that the first order plus dead time transfer function is something like gs equal to k divided by tau s plus 1 plus multiplied by e minus theta s, which defines the dead time. So we just define everything by the parameter, and then later on we will define this parameter in MATLAB. So I put k for the gain, and then tau as a time constant, and 1 as tau s plus 1. And then we don't put the disturbance, and we just put apply and then OK. What about the transport delay block? To add the time to our process, we make use of the transport delay. So we double click on the transport delay block, and it brings up its parameter window. Of the entire available parameters that we have, time delay is important for us. And then, since we can define the parameter later for our purpose of controller tuning and process model, so we just define this as a theta parameter, and we define it later. The other thing is initial output, initial buffer size, and initial output gives us default value that the block outputs until the simulation has caught up to the initial delay. Until the simulation has run theta time unit, it does not have the past value stored up to output. So since we are dealing with deviation variables, so we leave this as 0. Initial buffer size deals with RAM allocated to the storing past value of the at the start of the given simulation. So for example, for the worst case scenario, this value would be too low, and MATLAB will automatically resize it for you, and then we'll give some warning messages. But don't worry for this. We leave it as it is as default right now. We apply and say OK. Let's go to extract the information from our simulation by sync blocks. So we may use this in our lab analysis. This is where sync category comes to play. A sync is any tool that allows data extraction from Simulink system to either work within the MATLAB or display it to the user in some meaningful way. For this lab, we will make use of the two workspace, so as we discussed previously, and also the scope blocks. The two workspace block export the value of the selected variable on MATLAB workspace after the simulation has been completed. The scope block allows real-time monitoring of a selected variable during a given simulation. So for this experiment, we will want to monitor the set point, input, and output, which is the output's control variable. Therefore, we will need to drag 3 workspace blocks in our Simulink window. One might think that we would also need a scope block, but a 3 scope block, but we will see shortly that we can combine the set point and output signal to 1 scope. So we just need 2 scope blocks that we drag it to our workspace. So now is the time to connect them to the block diagram. But you see that the block line between the, the black line between the blocks, it shows that they represent actual information flowing through Simulink, while blocks themselves act only as transform this information. So I will connect workspace to this. The other one is for input. The other one is for output, and I connect it to this one. We will connect the scope later, but the workspace block, as explained previously, the workspace block exports our simulation variable to MATLAB. By double-clicking each workspace block, we may format the data further. So the most important block that we want is variable name. So for this example, we name the set point as SP, and then we can change the save format as array instead of time series, and the sample time 2.1 as is required, and we say apply and OK. So we will do the same for the other workspace as well. We change this to input array. Sampling time by default is -1, but we change it to our desired one. So we say apply and then OK. We change this to output and then change the same format to array and sampling time to 0.1. Oops. Change to array and sampling time 0.1, then apply and OK. After we did all these things, we go to the scope block. Once we have completed the run in Simulink, we can view the trajectory of selected variables using a scope block. So to do this, we simply double-click on desired scope block. First, I connect the scope block for the set point, and I double-click on it, and I will see there is a window. Actually, we show the changes of signal based on time. Sometimes the graph may not be initially sized properly, so to fix the issue, we press the auto scale, which is here, and then we can fix the size. Signal routing block. There is another important block here, which is signal routing block, and we have a mux component or block here. We can connect the scope, and we can, as the input, we can add two signals that we want to add the scopes together. So we want to see the scopes of the set point and output together with mux. The mux blocks allows the combination of individual streams in MATLAB into vector streams. This can be help us to see both signals at the same time. For this lab, we will use it to combine the set point and output signal onto one scope. As we saw. Also, I want to see the time in the system. So for sources, I will have the clock here. I want to send this to the workspace in order to keep the same size time that is used in workspace here. I go to the sync and I select the workspace and I connect time to workspace. In this workspace, we will do the same. Instead of variable name, I will select time, and it should be saved as array and sampling time 0.1. So we select apply and then OK. First we save this before anything, and then we check that step was as we defined previously, step time 50, and it started from 0 to 5. Okay, now let's define the parameters in the system. But before that, let's do the setting of simulation preference. Now our model is built. We are almost ready to simulate our process. The final step is preparing our model, adjusting the internal setting of the Simulink. So what we have to do is that we go to the simulation and we have the model configuration here and we click on it. So then a new window will show up and we will see that we can select a solver. As you see, we have a solver here, and we change it from the ODE or auto to ODE 23TV because this is for stiff actually cases. Once we change this, there is another thing that we have to change by all parameters. Selecting on all parameters, we change the relative tolerance from 0.10 power minus 3 to minus 8 to improve the accuracy of our simulation. Finally, we will want to adjust the simulation time to a reasonable value so that our system will do these changes to 900. Actually, I would say apply and OK, and then I change the time to 100, 1000 or 900. So then we apply everything and then we close it. So we save this file, and then now is the time to define the parameters in our MATLAB code. Close this, and then here we define the parameters in MATLAB code. As we see that we initialize a storage array, output save and input save, but our system, as we actually discussed previously, I mean, this is the example that we have. This is a liquid storage tank with some delay, but after doing the material balance over this tank with some linear control valve at the end of the line, we got and then after Laplace transform, we got this transfer function between the H and Q. These are actually deviation variables, and we got K equal to 0.12 and tau equal to 1128. Also, so we defined K tau as this, and we have some, for example, time delay in the system. So then we define, based on the way that we want to do the tuning, it would be like set point tracking, or based on another method which is for simulation or any purpose that we have. For example, IMC PID that we have, we can define the KC tau I and tau D that we want. So we run this parameter. Oh, actually we have to change this because the simulation name, Simulink file that we have has 0.4 as the name, and then we run this. After we run this, we go to the Simulink and we run this again, and then we see in the scope that this is the response of the system to the step. We can change the step from final value of 5 to 1 and apply it and run it again. After we run it, we will see that this is the response of the system, and this is the step that we have to the system, and this is the response of the first order plus dead time and then this is the result that we have. Thank you for watching this video.